Hi everyone, I'm Luke DeSmet, Technical Support Engineer at Oros. Thank you for taking the time to watch this tutorial video on the use of RT60 with interrupted source.
RT60 or reverberation time is used for room and building acoustics and sound power measurements to characterize a room. It corresponds to the time needed for sound to decrease 60 dBs after the interruption of the noise source or after an impulse noise, like a gunshot. Because of the background noise, this generally cannot be measured directly, so it is usually interpolated from the T20 indicator, which measures the time needed to decrease 20 dB, or from the T30 indicator, which measures the time needed to decrease 30 dB. In this tutorial, we'll show step-by-step how the NVGate model measures RT60 using the interrupted source method, which has been built using two microphones to measure the sound level in the room. How to automate the measurement procedure to start and stop the noise source using a loudspeaker connected to the analyzer's output, and how to use the dedicated Excel sheet for the final computation of RT60. As shown in other videos, it is possible to use an impulse source by modifying the settings shown in steps 5 and 8. The first step to create a setup is to select the transducers used. In this example, for an RT60 measurement, we will use the two microphones inside the room. The accelerometer on the door and the microphone outside are connected for sound insulation measurements. We select the transducers used. They have been previously registered in our transducer database. And then we change the input labels to be able to identify them easily. We now open the results overview window. In the 1/n octave plugin tab, we create a waterfall of average spectra for the first microphone. Display the 2D projections. Create a dedicated layout for the second microphone. Where we will also display the waterfall of the average spectra. And display the 2D projections. We can switch from one layout to the other using the layout arrows. We access the plugin settings from the results window. We set an exponential averaging with the time constant of 20 milliseconds in accordance to ISO 3382. In the analysis ribbon, we can change the waterfall depth to collect 1000 spectra. In the Measurement tab, we adjust the sampling frequency to 51.2 kHz to get a signal bandwidth of 20 kHz. Then, we will set an output signal from the Acquisition tab. We select a random noise to be generated on the output 1 of the analyzer. We adjust the upper frequency of the random noise to 20 kHz. In the output settings, we reduce the time to generate the noise and mute the output for the moment. Now I will show how to create shortcuts to specific settings. First, we display the control panel and open the Customize Control Panel window, where we create a new tab for the settings. We then select all the settings one by one that might need to be changed for the acquisition of reverberation time, like the total number of slices that will be collected in the waterfall. We change the label of the setting to recognize quickly what it represents. In the 1/n octave plugin settings, we select the mode of the CBB filters that can be octave or 1/3 octave. We also add the random noise parameters as the type of noise that is usually white. The RMS level of the output signal, and the mute all setting that will be used to start or stop the generated noise. Now the selected settings are accessible from the control panel. We can manage the macros from the Tools ribbon. We select the RT60 interrupted source macro and open its properties to assign a keyboard shortcut that can be used to launch the macro. In this example, it is F2. Then we click on Edit to see the actions performed by the macro, like unmute the white noise, wait for stabilization of the white noise before starting the measurement, mute the white noise after a few seconds, and finally stop the measurement after the decay of the noise. We press F2 to launch the macro. The output noise is generated for 5 seconds. Then the measurement starts. The noise is stopped and the measurement is stopped. We can then see the collected spectra for both microphones and the decay curves. Now let's export the waterfall results to compute the RT60 in the dedicated Excel sheet. In the workspace, we select the results to be exported. In the export window, we choose the text format and check in the text export preferences that one file per result will be generated. We choose an output directory and launch the results export. In the Excel computation file for RT60 measurements, we select the waterfall's data measured at input 1. The data is being imported into the dedicated sheet. We now activate the position 2 sheet and import the waterfall's data measured at input 2. The computation sheet is being refreshed with the additional data. The average level of the 2 microphones is computed in the dedicated sheet. The decay curve of each 1/3 octave band can be found in the overview sheet. In the Overview tab of the Excel sheet, we look at the decay curves for each 1/3 octave band to identify the time and the amplitude range of interest. Then we adjust the bounds and steps of the X and Y axis accordingly from the Settings tab. In this example, we'll look at the decay curves from 2 to 3 seconds with a step of 0.1 seconds. The amplitude of the sound level varies between 10 and 90 dB. We keep an amplitude step of 20 dB. After clicking on Set, we can see that all graphs in the overview sheet have been adjusted. In the Overview tab, we take special care of the bands where the indication difference T20 over T30 appears, which means that the difference between both computed indicators is higher than 10%. Let's begin with the 125 Hz band. In the corresponding sheet, we have a better display of the decay curve. We change the calculation mode to Auto T30, compare the computed regression line with the one of Auto T20 mode, and finally choose the Auto T30 mode as it better fits the decay curve. Then we go back to the overview sheet. Let's now focus on the 250 Hz band. We activate the corresponding sheet. Here again, we switch from one auto computation mode to another to choose the one that generates a regression line that better fits the decay curve. In this case, this is Auto T30 mode. Let's go back to the overview sheet. We'll now focus on the 400 Hz band. We therefore go to the corresponding sheet, and we try both auto computation modes. Auto T30, which results in an RT60 of 0.6 seconds, and Auto T20, which results in an RT60 of 0.5 seconds. Unfortunately, no one is very satisfied with the curve fitting. In this case, it is possible to freely set the start and end points used to calculate the regression line thanks to the manual computation mode. The regression line now better fits the decay curve. Back to the overview sheet, we visually check that the regression line fits the decay curves for other bands. In the Report tab, we find a table with the computed RT60 values for each 1/3 octave band. The calculation mode T20, T30, or manual used for each band is indicated to the right of the table. We can adjust the minimum and maximum frequencies that we want to use for the computation of the global RT60. The report is now finished.